Hello, warriors. This is Miss Lemons, and today we're going to be talking about bond enthalpies. But before we get started, let's go ahead and revisit the law of conservation of matter. Matter cannot be created or destroyed, only rearranged. So, how do we know this? Well, if we look at this image here of a reaction between C2H6 and Cl2, we end up getting C2H5Cl and HCl. Here's the deal. We know that the bonds of the reactants are going to be broken and that the bonds of the products are going to be reformed. And what's happened is that the atoms have just been rearranged, switched around. We can't just start with 4 carbon atoms and end with 2 carbon atoms. Where did the other 2 carbon atoms go? So we've actually practiced balancing chemical equations to account for the law of conservation of matter. We can also see it here without balancing this equation because it's a 1 to 1 to 1 to 1 ratio. See, the H and the Cl have been flip-flopped. These 2 bonds have been broken. So the bond between carbon and hydrogen has been severed, and the bond between chlorine and chlorine has been severed. And then the chlorine and the hydrogen swapped places, and new bonds were reformed. So when we're looking at the same exact equation, when we're talking about enthalpy anyway, it does take energy to break bonds. And I like to think of this as actually breaking or snapping a stick. If you snap a stick, it takes energy to break that stick. In the opposite fashion, when bonds are formed, energy is released. And I like to show that with these little lightning bolts heading out of the system or exiting the system. So we can safely say that breaking bonds is an absorbing energy. So it's an endothermic reaction because we've got this energy that is entering the system. It needs energy to break those bonds. And that forming bonds is exothermic, meaning that it releases energy or energy exits the system. So when we calculate the actual change in energy, we can use this formula. How we say this out loud is that the change in enthalpy is equal to the sum of all of the bond energies broken minus the sum of all of the bond energies formed. So this sigma formula is a little weird looking, but that just means add all of the values together. And the values we're talking about can be found in this table. Now, don't worry, both this formula and the table will be provided to you on your test. So no need to memorize, just know what you're doing with them. So you can see here that on our table of bond energies, we have all sorts of bonds. We even have double bonds and even triple bonds. So if we look here, we can see that, for instance, an OO bond, single bond, would require 204 kilojoules per mole of energy to break. But if we had a double bond between 2 oxygens, it would take 494 kilojoules of energy to break. Now, here's the thing. If you think about what it takes to break 1 stick versus 2 sticks, it takes more energy to break 2 bonds or 2 sticks than 1 stick, right? But also note that 204 and 494, that is not an equal 1 to 2 ratio. So you can't just assume that because it's a double bond, it is twice the amount of energy needed to break that bond. So more bonds means more energy, but make sure you don't just assume what the value is. Come back to your chart and use the number given to you. So let's try a practice problem. So if we look here, we've got 2 moles of water that will decompose to form 2 moles of hydrogen and 1 mole of oxygen. So first we're going to look at the bond of all of the energies broken. I'm going to break every single one of my bonds here. I have an HO bond, an HO bond, an HO bond, and an HO bond. And I actually like to cross them out as I go to keep track of which ones I've actually accounted for. So there are 4 OH bonds. I'm going to look at my chart to figure out what the OH bond value is. And I think I have it right here, 464. For every single one of these bonds, we need 464 moles of energy or kilojoules of energy to break that bond. So because I have 4 of them, I'm going to multiply that value by 4. Once I multiply that value by 4, I get 1,856 kilojoules. We're going to do the same thing for the other side. Here I have an HH bond and another HH bond. So I have 2 HH bonds. I also have 1 OO double bond. That is not two OO single bonds. It is a double bond. So I know that I'm going to be multiplying this value by 2 and the value for oxygen by 1 because there's only one oxygen bond. That's double. And then we also have 2 single hydrogen bonds. So we're going to look at our chart. An HH single bond is 432 kilojoules per mole, whereas an OO double bond is 494 kilojoules per mole. So we're going to go ahead and plug those two values into our equation. 2 times 432 plus 1 times 494 is going to give us 1,358 kilojoules. So now that we've figured out the energy of the bonds broken versus the energy of the bonds formed, we can now plug it into our wacky equation with the sigma symbols. That would be 1,856 kilojoules minus 1,358 kilojoules, which would give us 498 kilojoules. If you want to have more practice problems, feel free to keep going through the PowerPoint that's been posted on the website. Otherwise, this is the only practice problem I'm giving you today.